They're over there. We already took a quiz. You missed it. So. Just now. Well, we started at 11 o'clock. Yeah. Okay, if you could please click in. All right, so what I'm looking for, is everyone clicked in? Attendance? Remember, if you don't click in, that's what I'm going off of. So even if you were here all day but you never did that, then you're counted absent. So make sure that you're taking care of that every day. All right, let's talk about the quiz. Remember, I will always post these solutions online. So these will be posted later on today. The first problem was a basic substitution. The radicand x squared plus 1 is the u, because the derivative of x squared plus 1 is what? 2x. You got an x dx there. So your 2x dx, solve for x dx, you just get 1/2 du is x dx. You rewrite the integral, replacing x dx with 1/2 du. That's right here. Replacing the radicand with u, pulling the 1/2 out. 1 over the cube root of u is u to the negative 1/3 power. The antiderivative of u to the negative 1/3, you add 1 to negative 1/3, you get 2/3. Then you put 3/2 out here. You had the half that you started with in the beginning. Put that all together, here you go. Plus c, replace u with whatever it was. So that was the first problem. Second one was an integration by parts problem. And this is one where you didn't have a whole lot to choose from. You had to choose a u, you have to choose a dv, right? You have to. So the only thing to choose for u would be natural log x. And then the only thing you could choose for dv would be dx. The derivative of the natural log of x is 1 over x dx. The antiderivative of dx is the same as the antiderivative of 1, which is just x. And that's great because when you do ultraviolet, these two multiplied, you get just x natural log x minus integral. Look at what voodoo is. X times 1 over x is 1 dx. So these cancel out. You get x natural log x minus the antiderivative of 1 with respect to x, which is just x. So you get this. Write this down on your formula sheets. I'm going to allow you to keep this on your formula sheets. This one comes up enough. You know what I'm talking about when I say formula sheets, the ones that you can print off the web, right? The ones that you're allowed to use on the test. Just add it somewhere in there. The antiderivative of the natural log of x is x natural log x minus x plus c. All right, let's take a poll, see how you did on that quiz. If you feel like you did okay, yeah, give me a yes. If you feel like that was not a good quiz, give me a no. I'm sorry? It's just to get an idea. It's not scientific or anything. Okay, so my idea here was, 8 minutes I thought was a little bit, I don't know if that's quite enough time or not. I think it can be done. Some people finished it within that time. A lot of people didn't. What I'll be looking for is that you did at least one of those problems correctly, all right? Whatever problem that you did correctly, that'll be like 80% of the quiz. The other problem will be 20%. Let's just do it that way, okay? That way, if you got the first one right, you're going to get an 80, all right? If you got the second one right, you're going to get an 80 if you didn't get the first one right. I'll just kind of do what's best for you, okay? Yes? Well, I'll probably, on every quiz, I'll probably keep taking off until you remember. You have to keep in mind there are some instructors that will count the entire problem wrong if you forget C. All right, so I don't want you to go to another class and be like, well, my teacher never even cared if I put C or not. You know, it's there. You know, it's there. It's a constant of integration. Okay, let's go. We got a lot to do today. I usually ask if you feel like that was a fair quiz or not. I think it was fair, so we won't even discuss it. Here we go. This is where we were last time. We had done A, B, and C, right? The problem on the quiz, the one that was the natural log x one, was very much like which one? It was like B. B was the one where we couldn't choose anything other than this arc sine of pi x. That's what we choose for u, and for dv we chose x. If you go back and look at your notes, that's exactly what we did. So, okay, so let's pick up here. I still need to do part D, so that's where we'll start. This is one that I refer to it as the rabbit out of the hat integration by parts, because it seems like you just all of a sudden like get the answer when it looked like you were at a dead end. So what was one of the main things that I had said about integration by parts? That I wanted you to look at it as a what? See if anyone can get this. It's a formula, but what is it? It's, come on. Transferring of the derivative. It's a transferring of the derivative, right? You transfer it from one thing to another. You look at this, you say, I'm going to pick something in the new integral, it's going to be the derivative of that. I'm going to pick something here in the new integral, it's going to be the antiderivative, right? So you're switching the derivative. The problem is that when you look at something like part C, where we had t squared cosine beta t, we chose our u to be t squared because in the new integral, it was going to be what? 2t, and then we repeated the process, and the 2t in another integration by parts became just a 2, right, the constant. So we were able to like wipe out the t squared eventually by taking derivatives of it. What's the problem that we're going to run into if we approach this with the same logic? You can never wipe out e to the 2x. The derivative of e to the 2x is always going to be e to the 2x. And then when it comes to cosine, even if you take the derivative of it, you're going to get sine, right? Or if you go backwards, you're going to get sine. You know, right? You're always going to get sines and cosines. Neither one of these two are going to go away, right? However, it's still going to work if we try it. So let's go for it. I said you need to pick a u, and you need to pick a v. So I'm going to choose my u to be e to the 2x, and my dv to be cosine x dx. Now, the only reason I did that is because I like the antiderivative of cosine x. It's just sine x. So that's why I chose it. There's really not a whole lot more that I'm thinking other than that. And I really do like the antiderivative of e to the 2x. I mean the derivative. So let's complete the table. What's du for us here? 2e to the 2x dx, right? Because we took the derivative. And then the antiderivative of cosine x gives us our v, which is sine x. And now we just go to the formula. This integral becomes ultraviolet. So e to the 2x, bless you, sine x. That's our ultraviolet, uv, minus the integral of v du going across here, right? I'm going to highlight it this time because this will come up later on in today's lecture. Right? My ultraviolet comes from going across the top, right? That's how I get ultraviolet. That's this part right here. And then the next part comes from doing this diagonal, right? Now, the reason I'm saying that is because later on today, we're going to do a problem where we're going to do integration. We're going to make substitutions, and we will have already used U as a letter, and so we can't do ultraviolet minus voodoo anymore because U is already being used. So we'll have to do like W's here or something. So I don't want you to get fixated so much on the lettering of this as much as you see it as a pattern. Across the top is the first part, minus the integral of the diagonal here. You'll see when we get to it. All right, so what am I going to put next? Minus, you want me to pull that 2 out? I'd like that, please. Thank you. I don't have to, but I can. And then sine x dx. Okay, does everybody see how we did not really gain any ground here? We still have an e to the 2x. We have a sine x. That's not much better than this one was. All right, let's just try and apply the integration by parts again. Let's use the same u and v that we did before. Yes? Add I? Okay. Just want me to forget that? Okay. All right, so I'm going to make another integration by parts. I'm going to choose my u to be the same exact thing. U is e to the 2x, and dv is what? Sine x dx. Can anybody tell me why they think this is going to lead us to the answer? Like why this is going to get us somewhere? Yes? Yeah, the new integral that we're going to get, right, with this ultraviolet minus voodoo, right? The diagonal is going to look exactly like the original problem, isn't it? That's on the left side, like the left side of our equation. And somehow, luckily, we're going to be able to combine and move everything to one side. Again, hang tight. Let's see what happens. du is what here? 2e to the 2x dx. And our v going back up with integration is negative cosine x. Forgot to highlight my minus voodoo there. Okay, so keep in mind here, what were we working on with this little table? What piece of this up here? The yellow, but not including the -2 here, right? So I'm actually going to put this thing in a bracket because I want everyone to understand that that -2 is still floating out here in front, right? So it's algebraically, it's going to need to be passed through later. And I'm going to rewrite everything, the whole thing, starting with that green up there. E to the 2x sine x minus 2. Here comes a bracket. And inside this bracket, I'm going to put the ultraviolet minus voodoo that comes off of this, right? Because I'm replacing that whole integral with this formula. So what's ultraviolet for me here? Negative e to the 2x cosine x. And then, so minus, but look at what's here. I have a negative cosine, don't I? And I have a 2. So I know when I multiply these, it's going to be negative, but then I'm subtracting it. In the formula, it's subtraction, right? So it's going to turn into a +2. Integral e to the 2x cosine x dx. Close my bracket. Let's distribute that -2 through the bracket. E to the 2x sine x, what? +2 e to the 2x cosine x, then what? -4 integral e to the 2x cosine x dx. So that's where I am right now. Any questions? Let's take a poll, whether or not you're good up to this point. Okay, so this is kind of cheating, but no, it's not cheating, but let's just remember what this is. I'm gonna slide it to the right. This right here, this entire expression is what this original integral is, right? I'm going to put that original integral back over here. Right? That's what we're saying, that this integral is whatever this is, right? Minus 4 times, hey, look, that's the integral again, isn't it? That's exactly what's on this side. So what we're trying to figure out appears on the other side. And because of that, because this is equality, we always do with equality, we can move things around, right? We can add, subtract things from both sides. So how about I do this? I need to go to a new page, and I don't want to rewrite this, so let me grab this. Why don't I take this, and I come in here and I say, on the right side of the equation, I'm taking away 4 of those integrals, right? Well, let me undo that. Let me add 4 of those integrals over here. So I have no idea what the value of that integral is, but I can always add 4 times whatever it is. And I'm going to do the same thing to the other side. Now, what happens when you do this? On the right side, they cancel. And on the left side, you get 5 of those integrals now, right? So 5 of these integrals, antiderivatives, is equal to e to the 2x sine x plus 2 e to the 2x cosine x, right? And so how could I get this integral by itself right now? Just divide this 5 out. Divide 5 on both sides. And so what we'll get is integral e to the 2x cosine x dx is 1/5 e to the 2x sine x plus 2/5 e to the 2x cosine x. I just divided each of these terms by 5. So isn't this our answer? I mean, we have the antiderivative of this is a function. We have no more integrals over here. But there's one thing missing, plus c. And even though I never really had to do an integral to get this answer, I need to remember that there is always going to be a constant out there. So I'm going to say plus c out here. Just add a plus c. Okay, so do you kind of see what we mean by the rabbit out of the hat here? I mean, you're going along with your integration by parts, and it seems like nothing good is going to happen. Nothing good is going to come from it. And then it appears on the other side, and you're like, okay, great. But then you realize you can add the four of them to the other side. Now, just out of curiosity, what would happen if we would have gotten to this step right here? And you see where this -4 is? What if it was gone? What if that was not -4 and it was just plus? You could subtract it from both sides, but then you would get 0 on this side and your integral's gone. And what that means is you didn't do anything. You didn't make any progress, all right? Because it happens sometimes when you do integration by parts, it pops up on the other side, but when you try and do this, they wipe each other out and you're stuck. So you have to go and just try something different. Yeah, you just have to try something different. You've wasted your time. I don't want to say that, but it's a lesson learned. All right, that's the answer right there. Let's move on to the next one. So the next one is an integration by parts where you make a substitution first. I'm kind of giving it away when I'm putting it up here. But integral e to the square root of x dx. So let's rule out a couple of things here. I mean, it's obviously not power rule. Is this a basic formula? Don't we know what the antiderivative e to something is? Right? Yes, but we're missing the derivative of what's here, right? Derivative square root of x is like 1 over 2 root x or something like that. And it's not nowhere in here. It doesn't seem like a basic substitution is going to work in this problem, does it? Right? If I'm saying look for something in its derivative, square root of x, do you see its derivative there somewhere? Not really, right? So, but this technique, this example is to show you that sometimes a u sub to start will work even though it doesn't look like it's going to work. So I'm going to actually make that substitution. I'm glad you said that. I was going to ask you if you did, what would you have used? Okay, dx down here, and then you would have had to have done this, right? And then the derivative of this is what? 1 over 2 root x times e to the square root of x. And then up here is x, right? I'm going fast through this, but that's what would happen. And then your new integral would be this and this, right? Yes? Okay, and that would kind of maybe be a little bit nasty. It may work. It actually may work. But let's see how this u sub first is going to make this work out a lot nicer, right? You have to remember in mathematics, I mean, there's always the idea of trying to get from point A to point B, right? And there are many routes that connect these 2 points, you know? And what I'm trying to show you is, the path of least resistance. There might be another path where you take integration by parts and it does work out, but this method here will go pretty quick if you do this u sub first, all right? So I'm supposed to now take the derivative of this, right? Okay, so I want to show you something else that we haven't done. Do you agree that this is true? What do I do? Square both sides, right? Okay, let's take the derivative now of this. Let's just take the derivative right here. But we have to be careful because we have u squared, not just u. Derivative of u squared is 2u du. The differential, right? You have to remember you have to take derivative of the inside, derivative of u being du in this case. And then what's the derivative of x on the other side? Dx. You see how nice and clean that is? Compared to doing it this way, which would still get you there, if you did this, you would have done du is 1 over 2 root x dx. That still would have worked, okay? That's the way we did it last class. But I'm just showing you you could do it this way. So what I'm going to do is I'm going to replace my my square root of x with what? U, and I'm going to replace dx with what? 2u du. And let's see what we get. With this substitution, we get e to the u times 2u du, right? And let me pull the 2 out. Let me put the u in front of the e to the u. Let's take a look at this integral. Is that something that you're willing to go after now? How? How do you want to attack this? Integration by parts. Why? The transferring of the derivative, right? One of these you're going to choose, and when you choose it, you're going to be looking at its derivative in the new integral, right? If I choose my substitution, my function that I want to be differentiated, right? That u is the one I'm going to want to choose, right? Because in the new integral, what's it going to be? The derivative of that, which would be 1, right? See what I'm saying? Now this one I choose as my dv, and I'll have to take the antiderivative. But do you see that I've run into a little bit of a problem with my integration by parts table? This what I was just saying. I've already used u, right? Like my original integral is in terms of u. So I can't use the formula u dv minus, I can't use this. So I need to rewrite it maybe and use different letters like w dv equals wv minus what? vdw? I mean, it's the same formula, but since I'm already using u, I can't repeat that. Understand? Pardon? I would avoid that because then u prime might mean derivative, right? I mean, yeah. Yeah. You could also just switch letters. I mean, whatever you see is, as fit for you. Yes. You could. Yes. I'm showing you what the standard approach is. Just use a different letter. Just apply the formula to a different letter. If you want to do subscripts or dashes or, highlight it in different colors, as long as it comes out, no one's some code, hieroglyphic, some code that only you understand. All right, so what I'm going to do is I'm going to say that W is going to be the U, okay? And my dV, I'm going to use V because I don't have a V anywhere else. My dV is going to be the other function, which was what? E to the U du. And now let me complete the table. What's the derivative of W? Well, dW is du. Right, so I'm taking the derivative here. And then now I need antiderivative to go up. So I'm going to have V is what? E to the U. The antiderivative of e to the u with respect to u is just e to the u. And this is what I was talking about earlier. When you're going to now write the formula, you don't want to look at it as ultraviolet anymore, right? This is like what? Ultraviolet or something. It's not the same thing. It's WV, right, minus integral, what? V dW. So that's why if you just understand the pattern in the table, it's a little easier to apply it when you change letters. I hope that makes sense. Let's see if that makes sense. Yay or nay? So let's just write down the new integral. I have a 2 out there. Don't forget that 2. And then brackets, what? U e to the u minus integral e to the u du. Close the brackets, right? What's the antiderivative of e to the u? E to the u. See, that's a nice integral right there, right? And then plus the constant. I'll distribute the 2 through. Forgot to distribute the 2 through. Plus my constant. So this e to the u is actually what this entire antiderivative is. Right? Goes right there. Then the 2 came through. Now we have to switch back. What was u? Okay, don't forget, you've got to get back to your original variable. So u is square root of x. So this is 2 root x e to the root x minus 2 e to the root x plus some constant. If you wish to do so, you could notice that both of these have some common factors. You could rewrite this 2 e to the root x times, in parentheses, root x minus 1 plus c. All I'm doing is factoring out a 2 e to the root x from both of these, and then I'm left with this. Either way. Okay. We're going to move to the next problem. The last example of integration by parts that I'm going to give you is an example where what we're going to do is we're going to create what's called a reduction formula. This is one of the more complicated, not complicated, but, well, you'll see. I mean, it's just not as straightforward as the ones that we've done. There's a little bit more involved here, all right? The idea is this. We would like to know if we can come up with a formula, just a formula for taking the antiderivative of sine to any power. That's what we'd like. And I'm going to add one little thing to this. I need that n to be 2 or higher. All right? That's what I'm going to go with here. So I'm going to write that down explicitly for you. Let me make sure that's the way I want to do it. Yeah. So I want to find what the antiderivative of sine to the n of x's dx if n is greater than or equal to 2. The antiderivative. So really, we don't have much to choose from except integration by parts, right? If we choose this whole thing to be our u in our table, right? If I choose the entire thing, don't write this down, just listen. If I choose that, then what's my dv have to be? dx. And then when I go up to v, what am I going to get in here? An x. And then what's the derivative of this going to be? So this is chain rule. N comes down. You then subtract 1 power from that, so n minus 1 x. And then the derivative of sine x, which is cosine x dx. And the thing I'm really concerned about is what voodoo is. Because that's my new integral, right? The diagonal. And look at this new integral. It has x, it's got sine, and it's got cosine in it, which to me looks more complicated than what we started with, right? So that's not going to be the substitution or the integration parts we want to use. Instead, check this out. And do something a little different. I want everyone to realize that this original integral could be written like this. That's like me writing this down, top right corner, look. X to the n. Do you agree that that's the same as x to the n minus 1 times x to the first power? Yes, because you add the exponents, right? N minus 1 plus 1 would give you n. So what I've done is I've taken sine to the n power and rewritten it as sine to the n minus 1 power times sine to the first power. No, that's correct? As long as n is what? Bigger than 2 or higher, right? This will work. I mean, it would also work for 1 or higher. But, yes? Pardon me? Maybe. Why do I not care about if n is 1? If n is 1, what's the antiderivative of sine? Negative cosine. So, I mean, who cares, right? It's for powers of bigger than 2 and up, right? We want a formula for it. So, if I do it this way, watch what happens. I'm going to choose for my u, my sine to the n minus 1x. I'm going to choose for my dv, my sine x dx. And let's just see where this takes us, all right? What is the derivative of sine to the n minus 1 of x? Bless you. I'm going to need a little more room here, so I'm going to write it below it. N minus 1 comes out. Sine to the what? N minus 2, because you're taking 1 more away from that power of x. Then times chain rule. Cosine x dx. Yes? That's what the derivative of sine to the n minus 1 of x is. Now, do what? Well, I want to talk about that. What's the antiderivative of sine? We said negative cosine x. That looks just as complicated as the other one, but go back in the, well, if you didn't write it down, Can someone tell me the difference, though? What the other one had that this one doesn't? This has two cosines. The other one had one cosine, but the other one had something else. Yeah, there's something else. What did the other one have in it that this one doesn't? What was our dv? What was v? X. Just x by itself. No trig function, just x, right? Our other one had sine and cosine and an x by itself. This one doesn't have that, does it? It has sines and cosines, but no x by itself. Which is that's a huge deal. I mean, that's like two completely different types of functions. You've got the trig functions, and then you've got some, power function, linear function attached to it. We don't have that here. All right, so let's just grind this out. Let's write down what this is. And this time I'm going to bring the original integral down with me. The integral sine to the nx dx is equal to ultraviolet minus voodoo, which for me will be ultraviolet, negative, you want to do the cosine first? Cosine in front of what? Sine to the n minus 1 of x. That's ultraviolet. That's these two right here multiplied together. Okay, minus the integral voodoo. Did I put minus? I should probably just put what? Plus, because this one was negative, this one was positive. So I should put a plus here. And then, do I have any constants here? N minus 1 is a constant, right? N is a number. No one's telling me what it is, but n is an integer bigger than 2, or equal to 2. So I'm going to pull the n minus 1 out of the integral. I should probably state that up here. This works if n is greater than or equal to 2, and n is an element of double struct z, which is the integers. That means it can't be a fraction. If n's a fraction, this isn't going to work. All right? What now? What's the integrand? What do I have in here? Sine raised to the n minus 2 of x times cosine squared x dx. And now you look at that and you're like, well, look, in order to figure out what sine to the n of x is, I am going to actually have to figure out what this is. And that looks even worse, doesn't it? Okay. But check this out. We have one of the most important identities in pre-cal, the Pythagorean identity. The Pythagorean identity says that any time we see cosine squared x, we can replace it with what? 1 minus sine squared x. Right? This cosine squared x can be replaced with this. And now what I'd like for you to do is entertain the idea of distributing this sine to the n minus 2 of x through this parentheses and tell me what you'd get. You get two terms, right? First one would be sine to the n minus 2 of x. The next one would be minus what? Sine to the n, right? Sine to the n. Because what you have the same base, right? The base of these two things is sine x. Sine x. You add the exponents. What's n minus 2 plus 2? N. I'm going to rewrite everything. I'll ask if everyone's okay with this after I write it. So I've taken this and distributed it through this parentheses. Let's take a poll here of whether or not you understand why the red distribution through the yellow becomes this. Make sure we're all comfortable with that. Okay, I got 12 people, 15, 16. I'm wondering if having the bars over there is discouraging people from being honest. I'm wondering, because the whole point of this is for you to be able to like say I don't understand without actually raising your hand. So I'm afraid that people are seeing like all the green. They're like, well, I still don't want to be the person hitting no. I don't know. Like I said, it's my first semester using those, so I don't know how this is, if this data is even valid. All right, now I've done this, but I mean, what's going to be gained from this? That's right. You see this? Sine to the nx dx is here now, isn't it? Remember what we did in that problem, the rabbit out of the hat, where we moved that integral to the other side? It's exactly what I'm going to do right now. But I need to first release this integral, release this from this. So I have to distribute this n minus 1, and I need to break this two terms in an integral into two integrals. So that's what I'm going to write on the next line. I'm writing in red. Sorry, just the last color I had there. Minus cosine x times sine to the n minus 1 x plus, all right, this is going to be two different integrals. N minus 1 integral sine to the n minus 2x dx, then minus n minus 1 integral sine to the nx dx. So I'm splitting this up into two, distributing an n minus 1 to both. How can I move that sine to the nx to the other side? Add how many of them? N minus 1 of them, right? This is a number, right? This is like 5. So if I have minus 5 of these, I'm going to add 5 of those. But I don't have 5, I have n minus 1. I don't know what that number is. So I will add to both sides. I'm going to add to both sides n minus 1 integral sine to the nx dx. And then over here, add n minus 1 of these integral sine to the nx dx. What will the result of that be? I'll have how many on the left side? N of them, right? Because I have, like, let's say this is 5 minus 1, right? That'd be 4. And I'm adding 1 of them, so I'd be back up to 5, right? If this was 10 minus 1, that'd be 9. I add 1, I'm going to be back up to 10. This is n, take away 1. I'm going to add 1 more of those. I'm going to be back up to n. So I have n of those integrals on the left side. N of them. Here we go. N of those integrals. And that must equal negative cosine x times sine to the n minus 1x plus n minus 1 integrals sine negative n minus 2 x dx. My goodness. I need to go to another page. Go ahead. Okay. If I have, let's say I have an integral of something here, right? And I'm coming in here and I'm adding 4 minus 1 of those integrals, right? The n here is 4, right? That's what n is. So this is like saying I'm adding 3 integrals to one of these. How many would you have? 4. So if this is n, then n, I'm adding 1 more. It's just really like killing off that 1. And you're just left with n of them. No, well, no, it's there. You're not multiplying. It's not, the invisible one is with multiplication. right? You always have a fraction or something, you multiply by 1. You can always rewrite that 1 however you want. That's not what we're doing. We're just adding, we're adding coefficients. This is all we're doing. We're adding coefficients. One of the coefficients is n minus 1. The other one is 1. We add them together, you get n. Okay, next page. I need that integral by itself, so what do you suggest? Divide both sides by this number, which is n, right? Divide this by n, which means divide this by n, which means divide this, I'll just divide that by n, right there. And tell me if you like this or not. I'll be left with sine to the n x dx equals, I don't like that n down there, I'm just going to write negative 1 over n cosine x sine n minus 1x plus n minus 1 over n integral sine to the n minus 2 of x dx. And believe it or not, we are done. And I'll explain why we're done. I have not integrated anything. Okay, so let me explain something to you. I wanted in this problem to do what? Find this. It says creating a reduction formula. Let me show you how we use this. If you were to flip to the back of your book, if the person who owned the book before you did not tear out all the pages, then there's all these formulas in the back, right? I gave you the first 6 pages of formulas. But if you flip to the further, which I'm not allowing you to have on the test, there's more formulas. In fact, there's probably a book this thick full of formulas somewhere. But specifically, there's a formula, where is it? Formula number 73 is exactly this formula. Okay? That's the formula. And I showed you where it came from. Every single one of these formulas comes from some integration process. All right? It wasn't like the Moses with the tablets, you know, there was no like other tablets that had all the math formulas on them, right? Like, oh, by the way, we got this whole truckload of, you know, math, quadratic equation. No, we had to come up with this, right? So that's how you actually create one of those reduction formulas. Let me show you how we could put this into action, okay? Let me show you. Yes. I did, because n is a constant, I just put it out here in front. I put on the asterisk because remember that's like multiplication. Yeah, so I just put it out here. Got it? Okay, let me show you this in action. I've got to be quick here, okay, because we got to move on. Let's say that I wanted to do an integral like this. Integral sine to the 9th power x dx. Because of this formula, I know that this is going to turn into automatically what? Negative 1 over 9 cosine x sine to the 8th x, right? Plus 9 minus 1, which is 8 over 9, so 8/9 integral of what? Sine to the 7th power x dx, right? But I don't know what this is, right? I don't know what this is. But what can I do on this one? Use the reduction formula again. And this one would become what? So if I'll just do it in blue. It'll become negative 1 over 7 cosine x sine to the 6th x minus, or no, plus, what? 6/7 integral sine to the 5x dx. But I don't know what this is, right? But that could go down, and my new integral would be sine to the 3rd. And then I don't know what that is, and I go one more time, and it would be sine to the 1st. And the antiderivative of sine to the 1st is negative cosine. So I could eventually get to it, right? and you put it all together in plus C. There's your plus C at the very end. But do you see why they call it a reduction formula? You start out with a high power up here, you reduce it. Each application of the formula reduces the power until you get down to something you can handle. If n was even, then we would get to sine squared, right? So we haven't done sine squared. That's what the next section is. Yes. So that's a good question. Any other issues? Okay, make sure you go through all this homework. All right. I'm going to offer, let me see, where's my textbook? Here we go. I always like to offer a bonus for anyone who wants to prove a reduction formula. Just to turn in next class. Yes, like I'll add it to something. And the way I always do my bonuses, I try to do my bonuses, is that the fewer people that turn them in, the more it's worth. So if like you get it and you're like going and showing everyone around you how you did it, then everyone turns it in. Everyone responds, here's the answer to the bonus, then it's worth very little. But if you're like one of two people who get it right, it's worth a lot more. Okay? It encourages everyone to try it, but then at the same time encourages you to do your own work. So, and if it's something people are finding on the web, then well, I have 37 on there. 38, number 38's so number 35 and number 37 in your homework are both show these reduction formulas are true. But number 38 will be a bonus. Okay, let's move on. 38's a bonus. We have 40 minutes. We are moving now into the next section, which is 6.2. We already know the antiderivatives of sine and cosine. Just sine and cosine, we know the antiderivatives. Also, last class I showed you that if you take the antiderivative and you have a linear expression in there, I showed you with ax plus b. But if you just had ax in there, remember that we always have to have that 1 over a that pops out, right? Okay. So now what we're going to do is we're going to look at a strategy for doing integrals that have sine and cosine in them. Powers of sine and cosine, not just sine and cosine because we know how to do that, but like sine squared or cosine squared or sine to the fifth. Or maybe we have sines and cosines together, which is really what we're going to do, all right? So here's the idea. Here's a strategy. There's three different strategies, all right? The first strategy is this. If you have cosine with an odd power, then you do this. And I'm not going to read through that. When we actually do an example, I'll show you. I'll come back to this. The next strategy is if you have sine to an odd power. The next strategy is if you have sine or cosine to an even power. Then this is what you do. All right, so let's look at these examples, and we'll work through them. We'll go back to see which technique we're going to use and see how it goes. So what I want to be able to do here is find this without using the reduction formula we just proved. All right? I realize it's there, but on a test, you will not be able to refer to the reduction formula because you're not allowed to have that formula on the test, right? So how do you do this without the reduction formula? Here we go. Which of the cases does this fall into? Which of these scenarios do we have here? Sine to an odd power. Okay, if we have sine with an odd power, then what we're going to do is we're going to use the Pythagorean identity. We're going to factor out a single sine, which would leave us with an even power of sine. Then we are going to rewrite the remaining even power of sine using the Pythagorean identity. And then we will make a substitution of u being equal to cosine x. Oh, okay, sure, yeah, that's what we're going to do. What do you mean by that? Well, here's what we mean. We are going to factor out one factor of sine. So I want to rewrite this as sine of 4t times sine squared of 4t dt. You agree with that? I have factored out a single factor of sine, leaving me with an even power, right? So had this been 5, I would have factored out a sine 4t and been left with what? Sine to the 4th, which would have been an even power, right? No matter what, if this starts out odd and I pull one sine out, I'm going to have an even power of sine there. The next thing I'm going to do is use the Pythagorean identity to rewrite this even power. So this becomes sine 4t, and then what does this become with Pythagorean identity? 1 minus cosine squared 4t. And I need that in parentheses. dt. Now it says what? Make a substitution of, where was it? Right here. U is going to be cosine x. Or in this case, not cosine x, because we don't have x's. What do we have? 4t. Now, let's see why this is going to work. If I let u be equal to cosine 4t, then what's 1 minus this? 1 minus u squared. What's sine 4t dt? Isn't that the derivative of cosine? So isn't that du? So this is now becoming a basic substitution problem. I'm seeing something and its derivative there. So I'm going to let u be cosine 4t. du is what? Careful. Negative 4 sine 4t dt. So you have to remember chain rule, right? Derivative of cosine of something is negative sine of that, but then derivative of what's inside is 4. Do we have negative 4 sine 4t dt up here? Close, right? We've got sine 4t dt. We've got that. We've got it right here. It doesn't matter that that sign's on the other side of the parentheses, right? I mean, this is all multiplication. That sign can go to the back next to the dt. So I've got that. I just need to get rid of that negative 4. So what did we do last time? And divide, right? Negative 1/4 du is going to be sine 4t dt. And then the inside, I'm going to replace cosine 4t right here. I'm going to replace that. And I'm going to rewrite the problem. Why did I not grab more? Just curious. Why didn't I let my u be equal to the 1 minus cosine squared? Then the derivative of 1 minus cosine squared is way more complicated than this, right? You would have to account for that squared on that cosine. All right, rewrite the problem. What do you get? Negative 1/4. So this integral now becomes negative 1/4 integral 1 minus u squared du. And now, can everyone integrate that? That's just power rule now, right? Antiderivative of 1 is u. Antiderivative of u squared is 1/3 u cubed. Then you replace all your u's, and you're done. So at this point, I go dot, dot, dot. Because now, as soon as I get you to a place that we've done this, we don't do it, okay? You could do the rest. Questions? Let's see a vote on this, a thumbs up or down on that. Yes. You didn't see that this would, well, if you follow the technique here that you're being told to follow, like start with an odd power of sine, factor out one factor of sine, this substitution will always work. Okay, so you can kind of rest assured that that its derivative will be there, right? But that's only if you have sine to an odd power. If that doesn't happen, then you have to do something else, like the next problem. Okay, how about if we're trying to do integral sine squared x cosine to the fifth x dx. Notice we have sines and cosines together, right? So let's read through this. The first case is when we had cosine odd. Do we have cosine odd here? Yeah, we do. What was the next one? Sine is odd. Is sine odd here? No, so it's not that one. How about this one? Sine or cosine are even. Right? Yes. So why don't we try the first one, see if it leads us anywhere. All right? Try the first one. See if it works. Look, these are guidelines, okay? These are guidelines. We can attempt, ooh, that's misspelled. We can attempt using the following strategy, but you're not guaranteed it's going to work. Now, like I said, the sine cubed, that fell right into the format. It should go. At least you know what the substitution is supposed to be. Okay, so if we have cosine odd, we're supposed to what? Factor out a single cosine this time, and that leaves us an even power of cosine, and then we use the Pythagorean identity on that one. So let's see. I'm going to rewrite this as sine squared x. Then I'm going to factor out a cosine x, which leaves me how many cosines? Cosine to the fourth. Everyone agree with that? I'm now supposed to work on the remaining even power right here. And I'm supposed to use the Pythagorean identity. However, that's not cosine squared, is it? It's cosine to the fourth. Pardon me? Yeah, we're going to just write like this. There's two different approaches to this. You could write this as cosine squared x, all of that squared dx. Wouldn't that still be cosine to the fourth? And then what is cosine squared x going to become? Okay, so you agree it would be this. I don't like that cosine x. It's getting in my way. What am I going to do with it? I'm going to move it to the outside, over here with the dx. I just move this out of here. Because I actually realized that because of the technique, it says that I'm going to do this, I'm going to make a substitution of u being sine x, right? Which means the derivative of that would be what? Cosine x. So that's why I kind of know this is going to be my du. So that's why I moved it to the side. But what about this 1 minus sine squared x squared? I still have to resolve that issue. Or do you want to try and let u be sine x now? It's kind of your call here. You want to try it? You want to just try letting u be sine x and see what we get? Because I can keep simplifying this more and more. Let me try it, see what happens. What's the derivative of this? Cosine x dx. So I will be able to replace cosine x dx with du, yeah? And everywhere I see a sine x, I'm replacing with u. So this new integral becomes, help me out, u squared, parentheses, 1 minus u squared, quantity squared, du. And this integral can be done if I first expand this out. What's 1 minus u squared times 1 minus u squared? So FOIL it out. You would get 1 minus 2u squared plus u to the 4th du. So I just FOILed that, expanded it. Got these three terms after I simplified. And now I'm going to distribute my u through to each one. My u squared, sorry. So I've got u squared minus 2u to the 4th plus u to the 6th du. I should have already said dot, 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 okay? But I'm going a little bit further on this one. Now power rule. The antiderivative of this is 1/3 u to the 3rd minus 2/5 u to the 5th plus 1/7 u to the 7th plus constant. And now we replace u with sine x, and we're done. Please vote. While you're voting, well, I'll leave that up for a few more seconds. I hope that you're getting an appreciation for the fact that we are at day 5 in this class, right? Day 5? All right. Day 3. I introduced, oh no. Day 3, was it day 3? It must have been day 2. Yeah, there we go. There it is. On the second day of class, I introduced you to the power rule, right? Second day. Here it is, and that was like at the very end of the lecture. So we've had what? Since then, we've had class 3 and 4, right? 2 classes. And now, where are we? Now, we are at the point where that is the end of a larger problem, right? I mean, it's just a little piece. This is trivial to us now, right? It's trivial. And that's the way a course like this works. The stuff that we do today becomes trivial when? Not 2 weeks from now. Next class, it's trivial. That's the way it has to be in a class like this. So that's what makes it so hard, is because the pace of it is so fast. You have to master this stuff as we go. I mean, it's not like you're just going to cram for 10 hours before the exam. I mean, so I'm encouraging you to just do what I've said from the beginning. Work, 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 work. Shall we do another example? Sure. You're not ready to go. Cosine to the 4th beta t. You like the beta, don't you? Yep. Was it cosine? Did I repeat myself? In the previous problem, the one we just did, you're saying. We did, but we had a sine next to it, remember? That was the difference. See, we had a cosine in the 4th, but we also had the sine, and we had another cosine. That makes a big difference that we had that extra cosine here. So what are we going to do if we have an even power of cosine? Okay, class, I had to do a new little video on this problem because in my lecture notes, I had a typo in my notes. I had mistakenly put x here and put an x right here and put an x here and then put an x right here. Total mistake, oversight on my part. I should have known that. I've been doing this for way too long. But I had that in there, and then everything I did in that problem was therefore incorrect because it was based off the wrong formula. Therefore, I'm redoing this video, splicing it into the video from class, and I'm going to show the correct way to work this problem out. So here's the problem we had, cosine to the fourth beta t dt. I'm going to use the fact that cosine squared of beta t is equal to, from the corrected formula, 1/2 times 1 plus cosine 2 beta t. So what I do is I rewrite this integral. I write as cosine squared beta t times cosine squared beta t dt. Now I use this, and I rewrite each one this way. Since each one of those is going to have a 1/2 on it, I'm going to bring a 1/4 out because you multiply the 1/2 times 1/2. Then you'll have the 1 plus cosine 2 beta t times itself again. And now we will expand this. So we will multiply 1 times 1. We get 1. 1 times cosine 2 beta t, and then we add to that another one of those, so we get 2 cosine of 2 beta t. And then when we do the last multiplication, since they're the same thing, we're multiplying them together, we're squaring it. And then all of that dt. And now what we do is we see what we can handle here. I can take the antiderivative of 1 with respect to t, that'll be t. This one plus antiderivative would be 2, and then remember, this 2 beta is like an a, so I'm going to say times 1 over 2 beta, and then antiderivative cosine, which is sine of 2 beta t. So I can do that, and then the question is, how do I handle this? So I'm not ready to find an antiderivative of that yet. I actually have to go work on this one. So the antiderivative of cosine squared of 2 beta t will require another application of this formula up here, but instead of having beta t in there, we have 2 beta t. So we'll have to double the angle, which means that this integral will turn into 1/2 came out of that. 1 plus cosine, then double the angle, so 4 beta t dt. And then from here, you can integrate 1 and you can integrate this, and you'll be at the answer. So you got to get these two pieces here and then get your 1/2 distributed, put that answer right in here, and you'll have your antiderivative. I've got about 13 minutes. Y'all hang in there. All right, stepping away from those now, okay? If we have integrals involving tangent and secant, which we haven't had yet, then we already know that the antiderivative of secant squared x is tangent, because derivative tangent was secant squared. We knew that in Cal 1. And the antiderivative of secant x tangent x is secant x, because again, derivative of secant is secant tangent, Cal 1. Also from last class, we said if we have an a in there, we always have to account for that 1 over a, right? Okay. And now if you ever have secants and tangents together, raised to powers, there's another set of approaches, strategies for those, and they are the following. If you have tangent to an m power and secant to an n power, with n being even, we use the Pythagorean identity, we factor out a secant squared, which leaves us a power of secant, an even power of secant. We rewrite using this identity instead. So do you see this is very much the same approach, just using different identities? Understand? The substitution there would be tangent. If we have secant and tangent with n being odd, then we factor out a secant tangent and we do this. Now, I want to try and get, in the last 12 minutes, I'm going to try and do one of these. I don't think I'll have time for both. We'll see. We will almost be where I wanted to be at the end of today. I wanted to get through these, but we're not going to be able to. All right, let's try it. We have a new integral. We're going integral tangent to the fourth x secant to the fourth x dx. By the way, these integrals are going to come up for us next class. Like, if you're wondering when would we ever get, like, who's ever going to ask me to integrate that? in the next part of this section, we're going to do some integrals where you look at them and you're like, yeah, that's something I've seen in algebra before, and we're going to try and integrate. It's going to be very tough, and believe it or not, it's going to turn out to be a problem, something like this. So I guess I'm just trying to say, stay tuned. Like, there's a reason we're doing all this trig stuff. All right, so which scenario do I have here? Do I have n is even on the secant? Yes? This one says n is odd on the tangent. So I have an even on the tangent. So they're both even, but what I'm looking for is the secant. For the first technique, it says, what, n being even. If the secant is even, I want to try this. This one says, if the tangent power is odd, then I try this. So I'm going with that first one. Secant's even. Oh, what does it say to do? Secant's even. Factor out a secant squared. Then rewrite the remaining even power of secant using this formula. U will be what? Tangent. Let's try it. I factor out a secant squared. So how about writing the secant squared x times secant squared x dx? I'm going to highlight something here. The reason you do this is because you know that that highlighted part is the derivative of what? Tangent, right? So we're going to just now rewrite this secant squared using the Pythagorean identity. See, secant squared is what? What's that? No, you're looking at the derivative of that. I'm saying I'm using just the identity, the Pythagorean identity. What's secant squared x? 1 minus, careful. It's in here. It's in the notes right here. 1 plus tangent squared x. It's also on your formula sheet. So I'm going to replace secant squared with 1 plus tangent squared x. So I replace that 1 plus tangent squared x. Am I going to replace this secant squared with 1 plus tangent squared x? No, because that's the part I'm leaving alone. That's going to be my du. That's why we factored it out. So I still have next to that, I'll do it in red, secant squared x dx. And now let's make our substitution. U should be tan x, and du then would be secant squared x dx, which is exactly sitting here, right? Isn't that great? And I should be able to rewrite the whole thing. Integral u to the fourth, that's 1 plus u squared du. Dot, dot, dot. So at this point, you take that the rest of the way. Please vote yes or no on that. I'm actually going to be able to knock out the next one. So for this one, tan to the fifth secant cubed. What is the attack on this, according to what the note said? Tan is odd. So what does it tell you to do? Factor out a what? A secant x tangent x. So 1 secant x and 1 tangent x get factored out. So that'll leave me with tan to the fourth. And secant what? Squared. And then over here in red, because I'm just trying to color code what's going to happen, I'm going to have a secant x that I pulled out and a tangent x, and I'm going to have dx. And I put it in red because this is going to wind up being our what? Oops. This is going to be our du. And what is the u we're going to use in this one? Secant, because the derivative of secant x is secant x tangent x. But if I'm going to let u be secant, I need to get rid of the tangent to the fourth. right? So I'm going to replace this. How about we rewrite tangent to the fourth? Tangent squared squared? But what's tangent squared? I mean, sorry, what's tangent? Yeah, what's tangent squared x switched over using Pythagorean identity? Secant squared x minus 1. So just keep in mind, secant squared x minus 1 is tangent squared x. Squared means to the fourth power. And then the second secant squared is next to it. And then our secant x tangent to x dx. Make your sub. What's the sub? U is secant x. Derivative of that is secant x tangent x dx. Question? And now rewrite the whole thing. Integral. So u squared minus 1, quantity squared, then u squared, then du. And I'd use power rule on this one, right? After I multiply this all out. So I multiply this out, I get like u to the fourth minus 2u squared plus 1. Then I distribute u squared through, and I just use power rule in each term, antiderivative, replace my u with secant x, and I'd be done. I still have 4 minutes. Check it out. I didn't realize we've rolled through that so quick. Look at this next one. I'm give you your money's worth here. I'm going to stay to the end, okay? Every class pretty much. For some cases, we need knowledge of common identities, integration by parts, or just some persistence. All right? How about tangent x? Antiderivative tangent x. It's on your formula sheet, but we can get it on our own. Tangent is sine x over x, cosine x, isn't it? Basic u substitution here. Do you see something in its derivative? U is which one? Can you go either way? No. I want the derivative to be on top. I don't want my derivative to wind up in the bottom. So I would like the sine x dx to be my du. So I need to choose my u to be what? Cosine x. Du would be negative sine x dx, right? So I'm off by a sign. Negative 1. Negative du equals sine x dx. Help me out. How does this problem get rewritten? Negative 1. I'll put it outside. Negative 1. And then 1 over u du. Questions or not? We all good? Yeah, this is natural log, so we would have, I was going to do dot, 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 but wait. Natural log of the absolute value of u, right, plus c. Okay, what's u? Cosine x. Look on your formula sheet and tell me if we got it. On the formulas, this is formula number, let's see, what page is it? It's page 6, and it's formula number 12. Did we get it? Oh, wait, hold on. It's supposed to be natural log of secant x. So we have to just remember properties of logs. Remember this property, log, doesn't matter what the log is. X to the n power is equal to n log x. In other words, that numbers in front of logs can be pushed up as powers. Remember that? So this is really turning into natural log absolute value of cosine x to the negative 1 plus c. Now that's not the inverse cosine. That really means 1 over cosine, which is secant. All I'm trying to do is match the formula in the back. Just, I wouldn't want you to, you know, be like, hey, that's not right, or, you know, not be able to make the connection. There it is. I'm out of time. Didn't get a chance to get to these two. Wait. Yes, there is next week. I'm not going to, part B, I'm not actually going to show you. That's in your book. I want you to do that. Look at that yourself. For part B right here, the antiderivative of secant x. And the next one after that, secant cubed. These are both in your book starting on page 320. They are worked in the examples. I want you to see if you can follow that. I'm not going to start with those, right? In other words, we're going to consider that done. But I want you to read the book. It shows the actual antiderivative, how they did it. This one right here is tough. It's someone back in like the 1600s figured out that they could come in with a clever use of multiplying by 1 and get it to work. It's not something I would expect anyone in this class to have figured out. The secant cubed is a little easier to follow. Was there homework here? Yeah, but I'm saying for this section. So we can't do all of these. I will send you an email. When I get to my office, I will send you an email letting you know which ones you could do up to this point with what we have talked about, okay? But that's the homework assignment that will be for this section. Y'all have a good weekend. Turn in your clickers. Adios.